Screen
This
is visible, sir.
conference will
Screen is
now be
visible, sir.
recorded.
Yes, sir.
Are you able to see the screen?
Yes, sir. Yes, sir.
Okay, right. Thank you. Uh, Good morning, everyone. Mr. Qadir, just 2 minutes, I will start again.
Okay, sir. No problem, sir. No problem.
పవర్ లేదు ప్లస్ చేయదు కదా. So, good morning to everyone.
Morning, sir.
Okay, just thank you, Mr. Qadir, for the opportunity given to me, and I'm also very thankful to the college management having chosen me as a resource person to deliver the lecture on PILE Foundations Introduction to the Faculty Development Program. Just I would like to present. I would like to present on a talk on PILE foundations. So, as far as my knowledge is concerned, most of the participants are from civil engineering backgrounds. So, all of you are well aware about the deep foundations. So, one of the categories in the deep foundations is PILE foundations. So, in this particular presentation, you will be learning what are the types of piles and how the load carrying capacity of piles can be carried out, and how the load carrying capacity of group of piles can be carried out, and this kind of information you will be going to learn at the end of this particular lecture. So all of us we know very well that the pile foundation mostly preferred where the huge heavy loads are required to be transmitted into the deeper depths, and where the soil strata is very soft and loose in state. So those soils would not have much bearing capacity. So in that particular case, it is required to opt pile foundations. These pile foundations, based on the load action and based on the placement, these are end-bearing piles, friction piles, combined end-bearing and friction pile, and compaction piles. The four categories are there here, and the end-bearing pile is nothing but the load is shared by due to the end-bearing resistance only. In case of friction pile, the load carrying capacity is mostly derived by the surrounding friction, the shaft friction only. There is no end bearing in it. And the combined end bearing and friction pile is nothing but it is the pile in which the load carrying capacity can be derived from the end bearing as well as from the side friction also. And then the last one is compaction pile. These are the piles generally are installed in the loose granular material, so that once you drive the pile in that loose granular material like sand, then the soil gets compacted, and that's what it is called, compaction pile. And see the applications of piles, the pile foundation. This is a multi-story building in which the piles are located here. And in case of transmission towers, where the piles are subjected to wind loads, so the foundation will be subjected to overturning moments. So to resist from the overturning effects, it is required to go with pile foundations, if possible, the under-reamed bulb also, so that the uplift conditions can be very much controlled. And in the area of port and harbor, the uplift anchor piles can be provided. So in these applications, the piles can be, and also in the bridge foundations, we can go with pile foundations, and over there the bridge pier can be constructed, and like that. And where there is a then so see here, this is the particular pile pattern. The piles are embedded on hard strata. So the soils are loose in loose soil, and finally the tip is in the hard strata. This kind of piles are referred as end-bearing piles. So sometimes the piles are placed in the friction soils where you cannot get any end bearing. So the entire capacity is only due to the shaft friction. So these are called friction piles. So this is the combined end bearing friction pile. If you can see here, the pile is passing through the friction soil as well, is resting on the hard strata where end bearing is more. So this kind of piles are called combined end bearing and friction piles. And these are the compaction piles where the loose sand deposits in which the piles are embedded, so that the soil gets densified. So the conditions that require the use of pile foundations, you see here where the rock is socketed, a pile can be, and the friction can be mobilized here, and the end bearing is at the bottom, and this is the actual load applied. So in case of rock, we are not going to rely on side friction, but we only rely on only the end bearing resistance. So sometimes the soil gets eroded, so a loose soil, and when it is subjected to horizontal load, the soil reaction horizontally, it will be like this. So based on these mechanisms, the pile load carrying capacity can be calculated. And sometimes the piles are placed in a stable soil passing through the swelling soil. And then the swelling soil, the resistance, the swelling will be created here. And in case of stable soil, the friction will be acting downward here in this case. As the swelling soil makes the pile to move up, the pile portion which is there in the stable soil will keep the positive or negative friction. So like that, various loading conditions, and the steel piles, when you use it, its allowable load capacity can be calculated from the simple formula, that is area, the cross-sectional area of the pile AS, and the frictional resistance Fs is the allowable stress of steel, can be taken 0.33 to 0.5. This is the allowable structural capacity of steel pile, can be calculated like this. And the steel piles, the advantages and disadvantages are given here. And the concrete piles, usual length of the concrete piles 10 meter to 15 meter, and the load carrying capacity of the piles, the concrete piles will be around 30 tons to 300 tons. And the main advantages of concrete piles can be subjected to hard driving, corrosion resistant, and can be easily combined with a concrete superstructure. These are the advantages of the concrete piles that we can use it. And the concrete pile, the reinforcement configuration is like this. And the precast prestressed piles also will be used. And the usual length of these precast prestressed piles in the order of 10 meter to 45 meter. Their maximum length will be in the order of 60 meter. The maximum load that the precast prestressed piles can take is 750 tons to 850 tons. The cast in place concrete piles, their usual length will be 5 meters to 15 meter, and the maximum length will be 30 meter to 40 meter, and the load carrying capacity of cast in place concrete piles will be 20 tons to 50 tons. The approximate maximum load will be around 80 tons. So cast in place concrete piles, the advantages are relatively cheap and allow for inspection before pouring concrete and easy to extend. Those are the advantages of cast in place concrete piles, and the allowable load can be calculated based on this simple formula ASFS plus ACFC. AS is nothing but area of cross section of steel, and AC is the area of cross section of concrete. FS is the allowable stress in steel, and FC is the allowable stress of concrete. So that the load carrying capacity of the structural load carrying capacity of the piles can be calculated like this. And the cast in place concrete piles, the variety of piles here based on the method of construction and their procedure, these are the very number of piles that are available here. And in case of cast in place piles, the advantages are that initially economical, can be finished at any elevation. This is the advantage of going for cast in place concrete piles. The usual length of cast in place concrete piles is 5 meter to 15 meter, and the load carrying capacity of these piles will be 30 tons to 50 tons. There are timber piles, but the timber piles are not that common in India. But there are some specifications here. If you are interested, you can go through these specifications. And the load carrying capacity of structural timbers is like Q allowable equal to AP into FW. AP is the average area of cross section of the pile of timber, and the FW is the allowable stress on the timber, so that structural capacity can be calculated by using this formula. And the timber piles generally compression parallel to grain will be 6.04 megapascal, and the bending stress will be 11.7 megapascal, and the horizontal shear will be 0.66 megapascal, and compression perpendicular to grain will be 1.31 megapascal. So these are some of the specifications of stresses of timber piles. And then composite piles also very common nowadays. The wood, concrete, wood and the steel combinations can be used. Now, those are about the different types of piles and their behavioral patterns and all those we discussed. And now we go with estimating pile capacity. How to estimate pile capacity in a given soil and the type of pile. So there are certain formulas. As we talked about the friction piles, end-bearing piles, and both the end-bearing and friction piles based on the soil conditions and where the pile is resting accordingly. Sometimes we can only derive the actual capacity of pile from the frictional resistance and from both the frictional resistance and end bearing, and sometimes if the soil is passing through loose soils and where there is not much friction and resting on the hard strata, then in that case we only get the capacity mainly due to end bearing. So accordingly, the point bearing capacity or the actual capacity of piles can be calculated by using the formula called QU equal to QP plus QS. QU is the ultimate load the pile can carry in the soil, and QP is the end bearing capacity of pile or load carried at the pile point at the base, and the QS is the load carried by skin friction developed at the side of the pile. So total load, ultimate load is due to mainly the end bearing resistance as well as the skin resistance or sharp friction loads. So these two, and QS is very small in case of some of the soils where the friction is not mobilized. So in that case, the QS is taken as QP. So already we discussed these kind of things. In case of weak soil and hard rock, the capacity is merely derived by ultimate capacity equal to the end bearing resistance QP. And in case of strong soil and weak soil, in that case, the ultimate capacity is equal to QP, end bearing resistance in that particular strong layer. And in case of only weak soil, and the pile is also resting on weak soil, only the friction will be mobilized. So in that case, the ultimate resistance equal to the shaft friction load. The QP will become 0 here. The point resistance is 0 because the soil is passing through only weak soil and it is not resting on any hard strata. So the frictional piles, the overall formula equal to QU equal to QP plus QS. These piles are called friction piles because most of the resistance is derived from skin friction only. However, the term friction pile, although used often in the literature, is a misnomer. In clay soils, the resistance to applied load is also caused by adhesion. So the pile length can be calculated based on certain conditions. So we should know the capacity, and the length of the pile can be kept constant so that it can be variable. So based on the capacity and based on the actual load applied, the length of the pile can be calculated. So these are the formulas for ultimate capacity of pile, that is due to point resistance here and also due to skin frictional resistance QS. The failure pattern at the bottom of the tip level is like this. As per the Tetshagi, is a shallow failure, and as per the Vishik, it is a deep failure pattern that are noticed. The Mayer has suggested this kind of failure pattern at the bottom. So finally, the formula for ultimate capacity or end bearing resistance can be calculated from the shallow foundation bearing capacity formula. CNC plus gamma D NQ plus 0.5 gamma B and gamma. Here, the D is the width or diameter of the shaft. Q0 is the effective overburden pressure, is nothing but gamma into depth, and AB is the base area of pile. C is the cohesion of the soil. Gamma is the effective unit weight of soil. So wherein here NC, NQ, and gamma are the bearing capacity factors which take into account the shape factor. So in case of cohesive soil, this end bearing resistance can be written as cohesive soil. So Q0 NQ AB. So that is it can be written as QB AB. The QB is nothing but Q0 NQ. Q0 dash is the effective overburden pressure, that is gamma into the depth where we are interested to estimate the effective overburden pressure. So ultimate capacity is can be written as now like Q0 dash NQAB plus QF, and QU this is again can be written as this is the due to end bearing, and the QF is due to skin friction. The formula that we can write it AS is the shaft resistance shaft area, that is circumferential area from bottom to top, that is pi into D into L. Pi D is the circumference and L is the length of the pile. So that way the AS can be calculated. Q0 dash is nothing but the effective overburden pressure average value, and Ks is nothing but the earth pressure coefficient. Generally it varies from 1 to 1.5 and 3 also sometimes. That delta is the angle of wall friction. So by knowing all these parameters, you can easily estimate the ultimate resistance of pile, especially with respect to the vertical loads are concerned. So this Q0 dash NQAB is the due to point resistance, and AS Q0 dash KS tan delta is due to the skin friction along the pile shaft. So that way the ultimate capacity for the vertical load point of view on pile can be calculated in soil. So the angle of wall friction delta can be taken 0.5 times phi or 0.8 to 0.8 times phi. Phi is the angle of shearing resistance that you can estimate it from either from direct shear test or from triaxial compression test. So the earth pressure coefficient varies from 0.6 to 1.25, and the K value can be taken 0.5 for loose sand, and K can be taken 1 for dense sand, and the angle of wall friction delta can be taken phi, angle of shearing resistance, as per the code IS 2911-1979. For driven piles, loose to dense sands, the recommended value of K is between 1 to 3. So here again, for the corresponding to a particular delta value, the K value are given in loose sand and dense sand. If it is a steel pile and concrete pile and timber pile, so this particular table will help you to pick up the K value, coefficient of earth pressure, that you can substitute here. So in case of cohesive soil, for cohesive soil such as saturated clays, the angle of internal friction phi will become 0. So accordingly, the NQ value equal to 1 and N gamma equal to 0. So the formula will be simplified further. The end bearing in case of cohesive soil can be written as CB NC plus Q0 dash AB. Q0 dash is nothing but the effective overburden stress at a particular depth where the pile tip level. Therefore, the net ultimate load capacity of the pile can be calculated CB NCAB plus QF. So QE equal to CB NCAB. So this formula can be used, and where this alpha is the adhesion factor. It depends on the consistency of clay. The consistency of clay varies, alpha also will vary. For saturated clay, fully saturated clay, the alpha can be taken 1. In case of stiff clay, alpha can be taken 0.3, because in case of saturated clay, the soil is going to surround the pile surface effectively, so the entire friction will be mobilized. That's what the alpha can be taken 1. In case of stiff clay, as the soil is stiff, the soil is 100% is not going to adhere to the pile surface. That's what alpha can be taken reduced value 0.5 or 0.3, because 100% it is not going to surround the pile surface. So whereas the soft clay can surround the entire pile surface, and accordingly mobilization of adhesion is possible. So that's what alpha can be taken 1 in case of soft clay. So the NC, NQ factors which are required to substitute in the formula can be are taken from this particular graph. The angle of internal friction is given on x-axis, and the bearing capacity factors NC, NQ are given on y-axis. So for different L by D values, and the NC, NQ, N gamma values can be taken. And so that is a chart, you can utilize it. It's suggested by Merhoff in the year 1976. For clay soil phi equal to 0, the base resistance QB for piles in saturated clay soil may be expressed as CNC into area of the pile tip. So NC value can be taken 9 as per the Merhoff. The NC is suggested for phi equal to 0 soils 9. So the formula will become 9 into C into area at the tip level of pile. So C is the undrained cohesion. So alpha equal to 1 for soft clay, where the cohesion equal to less than 50 kilopascals, and as the cohesion C increases, the adhesion factor alpha decreases. Alpha equal to 0.3 for over consolidated stiff to hard clay. The skin resistance for the straight sharp, it can be for in case of erosionless soil, this is AS into A Q0 dash average effective overburden pressure at that particular layer, and KS is the coefficient of earth pressure, tan delta is the value, delta is the wall friction angle. So like this, you can calculate for every individual layer, and so that you can sum up so that you can get the total skin friction load. So the bearing capacity factor NC is 9 as per the Merhoff, and and also is suggested by Skempton that 9 CAB. So AB is the pi by 4 D square in case of circular pile. If it is a rectangular pile, B into L can be taken as AB. There are skin resistance by alpha method. Alpha, beta, gamma methods are available for the load carrying capacity point of view. The formula is here. The ultimate bearing capacity of piles in clay by using alpha method is CB alpha CUAS. So the alpha can be estimated from this particular chart. For the known value of undrained cohesion C, you draw the vertical line so that it will cut the curve somewhere, and draw the horizontal line. Whatever the alpha it gives, this alpha is required to be substituted in this formula. So this is called alpha method for the estimation of load carrying capacity in case of piles. Skin resistance by lambda method. This is the formula for lambda. As for the lambda method, the skin friction resistance can be calculated from this particular formula: lambda times Q0 dash plus 2Cu dash into AS. Q0 dash is nothing but the effective overburden pressure in a particular layer, average effective overburden pressure in a particular layer, and Cu is the undrained cohesion in that particular layer, and AS is the shaft area, shaft surface area in that particular layer. So the lambda frictional capacity coefficient, it can be obtained from the depth of penetration in meters. If the depth of penetration is known, suppose say 30 meter, then draw the horizontal line, it cuts here, draw the vertical line, so that whatever the value that the lambda you are going to get it here, that should be substituted in this particular formula, so that you will get the frictional resistance corresponding to a particular depth of penetration. This was suggested by Vijay Varkiya and Pope in 1972. So the beta method, alpha, gamma are over. Now beta method, the effective stress, this is also called as effective stress method of computing skin resistance. As for this method, the skin resistance equal to beta times average effective overburden pressure Q0 dash. So the Q0 dash is the average effective overburden pressure that you can get it, and the beta can also be expressed as Ks tan delta. Ks is nothing but the earth pressure coefficient. Delta is nothing but the angle of wall friction. This can be taken 2/3 of phi value. So this is the simple method to estimate the skin friction based on the beta method. So the The coefficient of earth pressure can also be calculated by a simple formula 1 minus sin phi dash root of ROC. ROC is nothing but the over consolidation ratio of clay. The over consolidation ratio can be 1 and above. So either sometimes it may be less than 1 also. So simply substitute in this formula so that the K0 dash can be calculated. So and the Mayer-Hop method, as for the Mayer-Hop method, the semi-empirical relationships are suggested for skin friction calculation. If it is a driven pile, the skin friction resistance can be taken 1.5 times Cu tan phi dash. If it is a bold pile, the skin friction Fs can be taken 100% times tan phi dash. By utilizing the value of 20 degree for phi dash for the stiff to very stiff clays, the expressions reduces to for driven piles 0.55 Cu, for bold piles it is 0.36 Cu. So these are sometimes empirical relations. You can straight away use it as per the Mayer-Hop's method for the estimation of skin friction in clay soils of piles. So application of CPT in pile design after D. Reuter and Beringen 1979, certain formulas are given here. So in case of sand, the minimum of F1, F2, F3 of these three, the minimum can be taken 0.12 megapascal, or CPT sleeve friction directly can be taken, or the cone resistance divided by 300 times can be taken. So like this, these empirical relations also can be followed sometimes to estimate the actual skin friction of a pile. The bearing capacity of piles founded on a rocky bed. So the simple formula that you can utilize here, the QU equal to 2 times N phi QUR. N phi is tan square 45 plus pi by 2. Phi is the angle of internal friction. So QUR is nothing but the unconfined compressive strength of the rock. So the whatever the rock samples that you got it, that you put it in the machine and test it for unconfined compressive strength, that it will give you QUR. So the N phi is from this formula. So ultimate capacity of pile, that you can get it from this particular simple formula in case of rocky strata, where the piles are embedded in rocky strata. The uplift resistance can be calculated from the formula WP plus AS into FR, where the WP is the weight of the pile and AS is the effective area of the embedded length of pile, shaft surface area, and FR is nothing but the unit resisting force or skin friction resistance force. So the uplift resistance of pile in clay can be calculated from this simple formula WP plus AS into alpha Cu in case of clay soil. WP is the self weight of the pile, AS is the shaft surface area, alpha is the adhesion factor, that is it can be taken based on the consistency either from 0.3 to 1. Cu is the undrained cohesion. So the board piles in sand, if board piles are constructed, the load carrying capacity can be calculated from this formula, the same formula, but in this case, the K is supposed to be taken 0.3 to 0.75, and usually it will be taken 0.5, and the delta equal to phi in case of board piles in dry sand, and the delta is reduced if slurry is used for boring. The unit point resistance of board piles is half to two-thirds of driven piles, half to two-thirds in driven piles. So the pedestal piles show 50% to 100% greater unit point resistance as compared to piles for pedestal. So these points are taken into consideration while estimating the ultimate capacity of board pile in sand. The board piles in clay, the formula is CNCAP plus alpha CAS. Alpha is 0.5 for straight piles excavated dry. Alpha equal to 0.3 for straight piles drilled with slurry. build shafts or build piles alpha equal to 0.3 and 0.15. For board piles installed in stiff fissured clay, the value of cohesion is reduced to 75%, the value obtained from the traction test. So sometimes we go for, apart from regular piles in strong soils, we also use the pile foundations in expansive soils, wherein the underlaid piles are very effective to use. And in that case, the ultimate load capacity is given as CNCAB plus alpha CAS dash. So AB is the area of the enlarged base and NC can be taken 9. The addition factor alpha can be taken 0.5, 0.4. The cohesion C will be taken as average value of the at the bulb level. Okay, so and the ultimate load for single bulb pile is this is the formula pi by 4 b square. B is the diameter, 9c, and plus pi by 4 b1 square minus b square. Here the b1 is the bulb diameter and b is the straight shaft diameter. Okay, so multiplied by 9c plus alpha c as. All the parameters are known to you, so that you can easily calculate, so that the ultimate load for single bulb can be calculated. For the ultimate load for 2 or more bulbs, the formula is as follows: pi by 4 b square into 9c plus pi by 4 b1 square minus b square. The b is nothing but here is the straight shaft diameter and b1 is the bulb diameter. So alpha CAAS plus CA dash ASB, like this. This kind of formula can be used, and the CA dash is the cohesion value at the bulb level, and C is the cohesion value in the straight shaft area. So ultimate load for 2 or more bulbs, this same formula is given here. AS is the surface area of shaft above the bulb, top bulb, and ASB is the surface area of circumscribing the bulbs between top and bottom bulbs, and CA is the average cohesion on AS, and CA dash is the average cohesion on ASB. So with that, so we discussed about how to estimate the load carrying capacity of piles and for different cases and different types of soils like sand and clay soils, and for different installation of piles like driven piles, board piles, and also we also have discussed how to estimate load carrying capacity for piles subjected to tension load, that is uplift capacity. And even when the piles are embedded in expansive soil or swelling type of soil, how to estimate the load carrying capacity for straight shaft and with a single bulb and 2 bulbs cases also we have seen. And now we go for a pile group capacity estimation point of view. Sometimes the single pile is not going to survive for the load which we apply. So in that case, it is required to go with 2 or 3 or more than 3 piles, so that the all the piles can be connected with the pile cap. That particular arrangement is called as a pile group. So pile groups are required mostly when the huge number of loads are required to be transferred onto the stronger strata. Right? So in case of single pile, once the load is applied, the stress mobilization contours are like this. And in case of group of piles, the stress mobilization contours are like this. So in case of group of piles, the stress interference will be present here and here. So this because of this stress interference effect, the group capacity will be less as compared to the individual pile capacity concept. So that way, the overall group efficiency will be reduced in some of the soils. So group of piles with the piles far apart. Sometimes if piles are spaced at maximum distance, the stress interference won't be there. So in that case, the efficiency of a pile group will be exceeding 100% or 100 or 100%. So these are the different pile group configurations, 3 pile configuration, 4 pile configuration, 5 pile configuration. This is a 6 piles, and this one 3 by 3 pile configuration, 9 piles. And you see here, this is a 3 by 4 pile configuration, like that. So we can have different configurations based on the load transfer aspect is concerned. So the converse Lebesgue equation can be used to find out the group efficiency of the piles, where so this is the group efficiency equal to 1 minus n minus 1 into m plus m minus 1 into n divided by mn, where n is the number of rows and m is the number of columns. So like that. So number of columns of piles, number of piles in the row, if you know, and the theta is nothing but the tan inverse of b by s. B is the diameter and s is the spacing between the piles. So by substituting all these conditions, geometric conditions in this formula, you can get the what's called the group efficiency of the pile group. This is suggested by converse Lebesgue. And the spacing of piles in a group, if a straight uniform piles, the spacing will be followed 2 times the diameter to 6 times the diameter. In case of friction piles, the minimum spacing should be 3 times the diameter. So end bearing piles passing through compressible strata, the spacing minimum should be 2.5 times the diameter of the pile. And the end bearing piles passing through compressible strata and resting on stiff clay, then the minimum spacing that we have to follow 3.5 times the diameter of the pile. So in case of compaction piles, the minimum spacing should be 2 times the diameter. So these are the certain guidelines as per the building code. So how much spacing that we can provide for different piles and different soil conditions. These 5 points are required to be keep in mind so that accordingly we can decide the spacing of the piles. So the pile group efficiency can also be calculated from this simple formula QGU divided by sigma QU. That is group capacity divided by sum of the individual pile capacities. So this gives you the efficiency of the pile group. So the efficiency of the pile groups in sand, the efficiency of 4 and 9 pile groups when the pile caps do not rest on the surface, the efficiencies of 4 and 9 pile groups when the pile cap rests on the surface, like different conditions, the pile group efficiency is given here. All right, so that it can be considered basic 1967. The pile spacing in diameter, and suppose this is the curve corresponding to 5. 5 is the 4 pile group, total efficiency with cap. And the pile spacing, suppose say 3, so that the efficiency will be 150%. So the pile group efficiency formula already we discussed it. This is the converse Lebesgue equation. The vertical bearing capacity of pile groups embedded in sands and Mr. Gulam. Hello. Mr. Gulam. Okay, good evening. Hello, Mr. Khadir. Hello, Mr. Kadir.
Sure. Sir, you can continue, sir.
Okay,
Sir?
ma'am. Okay, ma'am.
Okay,
Right.
sir.
That's what I'm looking at. So there's no response.
Yes, sir.
Shall we continue?
Uh, yes, sir. It is audible, sir. You can continue,
Okay.
sir.
Yeah. Right. Right.
Thank you,
Thank
sir.
you. Thank you. Right. Yep.
Okay, sir.
So as we are now talking about, the pile group efficiency. So one of the approaches that we can utilize for the pile group efficiency point of view is the converse Labarre formula, wherein we are in need of some parameters like the diameter of the pile and the spacing between the piles, and also the number of piles in the row and the number of piles in the column. So that information is available. It is easy for us to estimate the group efficiency of that particular configuration of piles. It is suggested by the converse Labarre. Now the other equation is that in case of group capacity estimation is concerned, especially in sand and gravel, we can use the formula group capacity equal to n times QU. N is nothing but the number of piles in the pile group multiplied by each pile capacity. So each pile capacity multiplied by the number of piles will give you group capacity, and this is applicable in case of sandy type of soils, and it is normally assumed that the efficiency falls to unity when the spacing is increased to 5 or 6 diameters. Since present knowledge is not sufficient to evaluate the efficiency for different spacing of piles, it is conservative to assume an efficiency factor of unity, and accordingly, this formula can be used for the group capacity of piles embedded in sandy type of soils. So it is very simple. You estimate the individual pile capacity, that multiplied by number of piles will give you group capacity. And this is the just a typical elevation of the pile, 3 pile group, and here 3 by 3 pile configuration is 3 by 3. In a row 3 piles are there, in a column 3 piles are there. So this is 9 piles total. This pile configuration is 3 by 3, and the resistance will be block resistance. You can calculate the total, the circumference, but all 3 piles together circumference